Welcome to Calculus. Today we will investigate calculating integrals using integration properties. We'll take a look at two examples. One is a linear function and the other is a quadratic function. So I want to investigate the linear function first. We're integrating from 0 to 4. So our x values are going to be restricted from 0 to 4 of the function 6t minus 3 dt. So let's start off by graphing this function. We're again limiting the domain from 0 to 4. So as I plot this linear function, its y-intercept's at -3. And that's actually where our interval for the domain begins, at 0. I'm going to use the slope to plot a second point. So 6 up, 1 over. My slope is 6. And I need to continue out to 4. So I can see from this graph that I'm going to exit the graph pretty quickly. So at 2, it's going to be at 9. And then I just have to estimate here at 3. It looks like it's going to be about there. Numerically, 9 plus 6, that should be at about 15. And then at 4, if I count 6 more, it's going to be up here at 21. So definitely my graph is leaving the screen there. But all we need the graph for in this case is an estimate. So I'm just going to draw this linear function again from 0 to 4. Very steep line. Again, it's slope of 6. And that is really the area that we're trying to calculate. If I just kind of sketch here, do a rough sketch, we want to calculate the area between this function and the x-axis. So I do note that there is a piece there that's going to be negative area. So again, I've got to calculate one as positive, one as negative. Now in our previous example, we looked at this task geometrically. We could do that here as well. But what we want to do today is look at it from the point of view of using properties of integrals. So the graph gives us kind of a rough feeling about what we're actually trying to calculate. But when we go to the calculation, let's use a couple of rules. So really properties. The first property we're going to need here is called the property of the integral of a constant. And what the property of integral of a constant says is that if I'm taking the integral from a to b of just a constant number, integral from a to b of c dx, that's going to be essentially finding, if I think about it as a function, if I had some c value, it's really just saying if I'm calculating from a to b of a constant, if I think about that as area, that's just a rectangle. And we know from geometry, rectangle is length times width. So definitely the length, or what we might call the height here, is going to be c. And then my width, which is on the horizontal here, is going to be b minus a. And that's a property that I can use to directly calculate a definite integral like this one. Well, we need one other property for this example. So I know that I've got some constants, but I do have a difference there as well. And so what I need to say is, can I, in a way, treat those pieces of the difference, 6t and minus 3, separately? And that is true. In fact, what we've got is called a property of linearity of a definite integral. And that sounds very fancy, but essentially what it's saying is that if I have the integration of potentially two functions added or subtracted, so let's just set it up, the integration from a to b, and let's just call that first function f of x, second function g of x. And if they're presented together as one function dx, what the property of linearity of definite integrals allows me to do is to then consider that as two separate integrals. So I can think of this as the integration from a to b of just f of x dx. And then whatever that sign is, this one is plus. If it was minus, it would show up minus there, of the integration from a to b of g of x dx. So those two properties are going to solve this for us almost entirely. We do need one final property. One thing I noticed with this integral is that it does include the linear parent function, which is represented by that variable t. It's linear because it's to the first power. So what we need is a formula. And we'll call this one the formula for integrating the linear parent. So what we're claiming here is that I've got the integration from a to b of just plain old x dx. Now I got to think in terms of an antiderivative for this formula. And really I'm thinking if I had a function and I took its derivative and the derivative was x, what would the original function have been? Well, we know that if I'm taking a derivative and it results in a linear function, it's going to start out as a quadratic function. So I'm going to put here that the original function would have been x squared. But I also have to think about what would happen to the coefficient. If I directly took in a derivative of x squared, it would be 2x. The old power of 2 would become a coefficient. But I don't want 2x, I just want simply x. So I need a fraction out here that would cancel that 2 from the power that's coming down as a coefficient. So I got to think 2 times what fraction would equal 1, and that's half. And that's my rule for the integrating the linear parent. Let me clean up a few items here because we do want to specify that that would be from 0 to b. Remember, the linear parent function does pass through the origin. And then if I use my boundary variable b, it won't be x squared. So let me just clean up the notation. By substitution, that's going to be b squared. Well, that's all we need to calculate the integration here. So we've spent some time just laying out 3 properties here. So we've got property of the integral of a constant, property of linearity of definite integral, and the formula for integrating a linear parent. So let's start by applying the linearity property. So what I'm going to do is I'll bring down that integral from 0 to 4 of 6t minus 3 dt. And I'm going to apply that linearity property. So I'm going to split 6t minus 3 into 2 parts. So the first part is going to be from 0 to 4 of simply 6t dt. And then because my sign is minus in between the 6t and the 3, I'm going to put right minus the integration from 0 to 4 of 3 dt. At that point, what I can do, and it's an additional property that tells me if I have a constant multiplier like that 6, that can pass outside my integral. So I do want to take one more step to write this as 6 times the integral from 0 to 4 of simply t. And I do that to isolate this so that it is my linear parent, dt minus integration from 0 to 4. Now I don't pass the 3 out because it's just a constant. There's no variable there. Once I've got those separated like that, I can apply my formula here. So if I'm calculating from 6 times the integral from 0 to 4 of t dt, that's going to equal 6 as a multiplier times, if I'm going from 0 to b x dx, it equals half b squared. So this is going to equal half my b value, which is my upper limit of the integration, is 4. So that's going to be 4 squared. So notice we're turning it into a numerical expression. Well, that takes care of that first integration. And now we got this second one, and I'm going to apply the property of integral of a constant. So my c here is going to be 3. And then my b minus a is represented by the limits of integration 4 minus 0. And that's going to be my area. So let's go ahead and calculate. We'll start with the first term here. 4 squared 16. Half of 16 is 8. 6 times 8 is 48. And then for my second term there, minus, well, it's going to be minus. And then 4 minus 0 is 4 times 3 is 12. And finally, 48 minus 12 is going to give us 36 square units. So the area from 0 to 4 for this function, 16 minus 3, is going to be 36 square units. So that was an example that was a linear function as the integrand. Let's take a look at a quadratic function as the integrand. Here we got the function from negative, well, we're taking the integral from -3 to 1 of the function 7t squared plus t plus 1 dt. If I graph this function, I really have kind of a very steep graph. So I notice that my coordinate plane here has a very extended y-axis. It goes all the way to 70. So what I want to start off with is just to create a brief table. And we're given t values from -3 to 1. So -3, -2, -1, 0, and 1. And let's calculate f at t. So if I calculate it out, plug in -3. -3 squared is going to be 9 times 7 is 63. Minus 3 is 60 plus 1. This should be 61. -2 plugging in for t. -2 squared is 4 times 7 is 28. Plus -2 is 26 plus 1 is 27. At -1, -1 squared is 1 times 7 is 7. Minus 1 is 6, plus 1 is 7. At 0, the first two terms are going to zero out. We just are left with the y-intercept of 1. And at 1, we've got 1 squared is 1 times 7 is 7, plus 1 is 8, plus 1 is 9. So let's graph this function, again, from -3 to 1. -3, we have a value at about 61. Got to estimate there on the graph. -2 is at 27. -1 is at 7. 0 is at 1. So that almost hits the x-axis, not quite though. And then at 1, it's at 9. So the function we're considering is this restricted quadratic. And again, what we're trying to calculate is what is the area between that curve and the x-axis. So again, just to visualize what we're trying to calculate with the integral is that shaded region. So a little different from our previous example. If we think about the sign, the entire sign of that red region is going to be positive. It's all above the x-axis. So again, we want to use some properties. Definitely we want to apply linearity. Again, that's the one that allows us to split up terms that are added or subtracted. So let's do that first. And we'll just start creating this here. So this is the linearity property. And I'll just abbreviate here, but again, just to indicate what's the rationale behind this change. So we'll write this as the integral from -3 to 1 of 7t squared plus, so I'm using plus because it's plus in the function, the integral from -3 to 1 of the linear parent function t, and then the integral from -3 to 1 of 1. So we're set for this second and third one. Those ones we have formulas for already. That's the constant property of integral of a constant. This is the formula for integrating the linear parent function. What's different for us is this squared term. So let's give one additional property, and this one is the formula for integrating the quadratic parent. And it's going to be like what we saw the formula for integrating the linear parent, but now thinking about the antiderivative that would result in x squared. So let's say what that formula is going to be. So we'll start off and say the integration from 0 to b of x squared dx. So again, I need to think in terms of antiderivative. If I have a function that's going to be differentiated and become x squared, the first thing that I got to think of is that the original function would have had to be x cubed, the cubic function. But if I differentiate just x cubed, that's going to be 3x, and I'm left with a 3 as a coefficient that's not there in the x squared version. So I got to think 3 times what fraction would give me a coefficient of 1. That's going to be 1/3. And again, because I've put this as the upper limit as b, I don't want to indicate that it's x. I want to actually say that that's the value of b, because we're dealing with definite integrals. They have a real x value where they start and a real x value where they end. Okay, so let's apply our properties and let's integrate this quadratic function. So I'll start off by, again, letting the constant 7 as a coefficient pass outside the integral. So I am going to write this as 7 times the integral from -3 to 1 of t squared plus the integral from -3 to 1 of t plus the integral from -3 to 1 of 1. So that's now set for us to calculate. So we'll start off here by applying our formula for integrating the quadratic parent. So that's going to be 7 times 1/3, I'm using my formula here, which again is substituting for that integral, times b. So my upper limit here is 1. Now I have an issue here. Notice that I'm not starting from 0. So I need to do a couple things before I can kind of zoom through this integration and really pick up a second property. So if I have, and really I need 2 properties here. So let me put these 2 properties forward. So this is the property of additivity of adjacent integrals. I'm sorry, not integrals, adjacent intervals. And what this will help me do is kind of partition this domain into 2 intervals where I'm considering from 0 instead of from -3. So let's say what this property says. It says that if I've got an integral from a to c of f of x dx, if I want to split that so that it has an kind of change in the domain so that I partition it according to a number that's between a and c, we'll call it b. So what we should say out here is that a is less than b is less than c, that's equivalent as the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So I can split the interval into 2. So let's apply that here. So what I want to do is my b value here is going to be 0. I see that 0 is between -3 and 1. So my next step is 7 times the integral from -3 to 0 of t squared And let me make sure to put my DTs. I forgot my DTs. And we'll do the same also with the interval from 0 to 1. So I do have to include that multiplier 7 from 0 to 1 of t squared dt. Now, there's one other thing that I need to do. Let me get my last two terms. So we'll wrap here, plus the integral from -3 to 1 of t dt. And the integral from -3 to 1 of 1. Now, I do need to actually back up here and do the same for my linear function. So I want to also apply the property of additivity of adjacent intervals here. So I'll again split that -3 to 0 of t dt plus the integral from -3 to 0. Let me back up there from 0 to 1 of t dt. And then I can bring my final interval plus the integral from -3 to 1. We're okay there to use that whole integral from -3 to 1. So there's my expression. Now, can you see the two parts that we need an additional rule for? It's these where I start with -3 and end in 0. I got two of those. So what I need is really to reverse the limits of integration. And what that is a final property for us. So let me just draw a separation line here so we don't confuse our properties with our calculation. So the last property we need is called the property of reversing limits of integration. And essentially what we want to do is just switch the 0 and the -3. Property of reversing limits of integration. So if I'm integrating from, so again, we'll say that A is less than B here. If I'm integrating from B to A, so that's kind of our setup here from -3 to 1. But notice it's flipped of f of x dx. Essentially, I can switch the A and the B, the limits of integration, and all it's going to change is the sign out front. It's going to become negative of f of x dx. So for me, for this two terms that we identified where we need to switch these limits, this property of reversing limits of integration allows us to do that. And essentially, we just switch the sign as we switch the limits of the integration. So my next step, and I'll put it in the light blue so it's distinct from our properties. So this 7 from -3 to 0 of t squared dt is going to become -7 of the integral from 0. So see, I switched that with the -3 of t squared dt. The second integral is fun because it's times 7 from 0 to 1 of t squared dt. Again, I want to switch the first integral term that governs my linear parent. So the first version was plus, so we'll change it to minus the integration, switch the limits. So instead of -3, I'm going to start at 0 to -3 of the linear parent t dt. The second one again is fine. It's the integration from 0 to 1 of t dt. And lastly, plus the integration from -3 to 1 of 1 dt. So that's ready now to calculate. I want to apply my formula to start, which is how to integrate the quadratic parent. So we're going to use this first property here. So I'm going to write the initial coefficient -7. And then I'm integrating from 0 to -3 of t squared dt. So that's going to be 1/3 as a factor there, so I'm multiplying a third times the upper limit, -3 squared, plus 7. We'll keep this color coded so we can see where we're applying the properties. So plus 7. Again, I'm integrating from 0 to 1 of t squared dt, so that's going to be, again, a third times the upper limit 1 squared. All right. Minus the integration of my linear parent now. So remember, that one was half times -3 cubed, or I'm sorry, squared. So I do see I've made an error here with my powers for the quadratic one. That should be, so I see it should be the cubic. All right, so we'll pick up again with the second expression for our linear term, plus half. This one's integrated from 0 to 1, so the upper limit's 1 squared. And then our last term here is going to be the integration of this constant 1. So remember how we do that is we put the constant 1, and then we're multiplying that by the difference of our two limits. So it's going to be 1 minus -3. All right, so we're ready to calculate and find the numerical area for under that curve. So let's finalize here. We'll finalize in green. So we're just going to multiply out. So -3 to the power of 3 is -27. And if I divide that by 3, multiply by a third, that's going to be -9 times -7 is going to be +63. For my second term here, 1 cubed is 1 times a third is a third. So this is +7/3. Okay, my third term, -3 squared. That's going to be 9 times a half is 9 halves, and that's minus. So this is going to be -9/2. And then for my fourth term, it's 1 squared is 1 times half is half, so +1/2. And then for my constant term, 1 times 1 minus -3, that's 1 plus 3 or 4. 1 times 4 is 4. So I see as I add this together, -9 halves plus half, if I group those guys, that's going to be -8 halves or -4, which is going to cancel out with my 4. So I'm really left with 63 plus 7/3. So I can express that in different ways. Let's express it as a mixed number. So 7/3 is 2 1/3. So if I add that to 63, should get a total area there of 65 1/3 square units. 65 1/3 square units. Well, thank you for joining for this investigation of calculating integrals, definite integrals, using the properties of integrals. See you soon.